Hello and welcome to the first official episode of From the Void Up, World Building with Science and Sociology. This is a world building guide for anyone who cares too much about the minutia, like me. I am your host, Tyler Hadar, and if we're all ready to go, let's start building. Today, we are going to be talking about the most basic step in deciding geographical designs, the plates. Plate tectonics drive the Earth's surface in terms of all mountain ranges, volcanoes, even down to what is ocean and what is land. This is really going to help you sketch out a scientifically accurate idea of where different geological structures occur, and I'll definitely come back to these base sketches later when I get to the little detail episodes for mountains, volcanoes, and earthquakes and whatnot. So let's get into the science of Earth real quick. The stuff we see and walk around on is at the surface, which is a nice, cool, very solid rock layer called the Earth's crust. The crust is essentially a little lifeboat on top of a very deep rock ocean. Well, solid rock ocean, but we'll get to that. The crust isn't a single lifeboat, though. It's more of a giant collage, like bumper cars running into each other. And these boats are the different plates. And together, they make up the crust. And it's the interaction between these pieces of crust, or actually their plates, that really makes the interesting stuff happen. Like mountains and volcanoes, which is the bread and butter of fantasy settings. Now, if the interactions between the plates is what makes the fun stuff happen, why do they interact? And how can we predict what will happen at these different intersections? And what does it mean for your setting? Let's review. So if you take a slice of the Earth like it's a layer cake, picture like a nice little V-shaped slice floating in space. At the very pointy bit is the core. This is coming straight from the center of the Earth, and it is solid iron, because the core is a moon-sized ball of iron at the center of the Earth, spinning horrifyingly fast. It doesn't drive the rotation of the Earth, but it does produce magnetic fields and is the center of gravity, both of which make it possible for life to live on this planet. The next layer is called the outer core. Surprisingly, this section is actually liquid. It's just liquid iron soup, and like we know for a fact that it's liquid, it is confirmed by scientists studying seismic waves and how they travel or don't through the Earth. Recording where types of seismic waves end up and where they don't, depending on if they're capable of moving through liquids, shows definitively that the outer core is just soup. Which brings us to the mantle, which despite what most movies and even sometimes documentaries show in imagery, is not soup. It is not a liquid. It is not made up of magma. It's not even technically red. It's just rocks. It's literally crystallized rocks. And they typically actually are green, although they are hot enough to glow red. So technically it glows red, but if you cooled it down, it would be green. They are just crystallized rocks rolling around and blending and pulling like layers of Play-Doh getting squished and pulled. And we know for a fact that it's not liquid because those seismic waves that can't move through liquids are always recorded to move through the mantle, but not the outer core. So this means that the mantle has to be solid. The mantle is all rocks. I don't know if anybody else picked up on that in science class, but I sure didn't. Shout out to the professor who posted his Geology 101 lectures on YouTube at Earth and Space Sciences X. Go check him out. His lecture's pretty good. For teaching me that after I'd already gone through high school, gotten a 5 on my AP environmental exam, I'm honestly surprised I have gotten so far thinking I know so much about earth sciences while not knowing that the mantle is not liquid. So I thought I'd reinforce this, because who else thought this? Like, it could be anybody, but not us, not anymore, because we now know that the mantle is rocks. It's just weird Play-Doh, like hot rocks, so hot that they move and bend despite being solid crystals. There's actually a whole recent, and by recent I mean like 2014, study that explains basically how solids can kind of act like liquids, and it's called disclination if you want to look it up. Very cool, but way more detail than what we need at the moment. Now, the upper layers of the mantle are where the interesting stuff happens. The mantle itself can be defined as one big layer if you're talking about its chemical composition. But if you're talking about the mechanical composition, there are quite a few different ones depending on the temperature and pressure of those different sections. So the mantle is mostly composed of different silicate rocks, but primarily rocks that one would call mafic or ultramafic. These are rocks that have minerals with tons of iron, magnesium, and calcium. One of the most frequent of these minerals is called olivine, which looks dark green, sometimes almost black, if it's in a rock called peridotite. So that's what the mantle would actually look like if you cooled it down, although it is glowing red hot like metal gets hot. So remember how I was saying that the mantle is like Play-Doh? It's not really that consistency throughout the whole mantle. The lower section is called the mesosphere, and it's more like actual rocks that we see, but they're moving very, very, very slowly. And then in the upper sections, there are two groups. One is called the asthenosphere, which is the really Play-Doh-y section. The mesosphere is less Play-Doh than the asthenosphere because it's under so much more pressure. They are both extremely hot to the point where these minerals should be melting, but the pressure keeps the minerals from completely deforming. It's also what makes the inner core solid, while the outer core is literally a liquid. And this is the concept of disclination. Go ahead and look up the details if you want, but we're not covering it. But where we really need to start paying attention for plate tectonics is the lithosphere. Because unlike the asthenosphere, this section is actually solid rock. It is a rock layer that the crust is built on top of. And actually, it's the gaps and breaks in the lithosphere that cause plate tectonics. It's like a mattress and a box spring. We sleep on top of the mattress, but it's actually the box spring that's resting on the bed frame. So the lithosphere is solid and is moving in chunks on top of the asthenosphere, and the crust is hitching a ride on top of that. So then we ask, why does the asthenosphere move? And this is answered by my favorite concept, convection cycles. Convection currents. Convection it's everywhere. These things are everywhere, and they're extremely important to understand because they're going to be coming up in the next few episodes, I can guarantee. So convection currents are these currents of movement that goes in a circle when matter heats up and cools. If you can look up a diagram, it'll probably make my explanation make more sense if you can see kind of a diagram of it, but I'll try my best to give a description here. So let's use some more food. We've already talked about cake, let's talk about some soup. Because soup is yummy, but also it cooks in a pot with lots of bubbling liquids. So the pot is sitting on top of something that produces heat, like a gas stove with fire. The fire heats the metal, and the metal heats the water at the bottom of the pot. This is through conductive heating. But now the bottom of the water is warmer than the top because it's closer to the fire. The hot water is less dense than cold water because the water molecules have so much more energy now. They're bouncing farther and farther from each other than in the cold water. More space between the particles means less dense, and less dense things rise. So that hot water then rises up to the top of the pot and leaves an empty spot below where the cold water sinks. The farther it gets away, it starts transferring that heat up into the air above and it cools. And as it cools, the water at the bottom is now getting hot. They start to switch places. So it heats, it rises, it cools, sinks, heats, rises, cools, and so on, and it's just a giant circle, which is a convection current. inside the Earth, it's basically the materials in the mesosphere that get super close to the core, which is even hotter than the rest of this place, where it starts to heat up and rises towards the asthenosphere, which then it's kind of like water letting off steam. The hot rocks transfers that hot energy into the asthenosphere, which takes the energy and starts moving about as it cools down. And this movement causes tons of friction between the asthenosphere and the lithosphere, the solid lithosphere. These are moving rocks, so this isn't like water pulling sand around in the ocean. These are literally giant rock gears in a very slow-moving clock. And with the energy of that heat turned into the moving around, then all of those rocks begin to cool and sink. And new hot rocks begin to rise up to take that place. Now this process takes ages, because these are rocks. They don't exactly just rise and fall like carrots in a soup. The time it takes for one particle to make a full cycle could be anywhere between 50 to 200 million years, which is a lot longer than the minute or two in a pot of soup, because these are rocks. Nonetheless, these movements easily drag around our little lifeboats floating on the very solid rock sea that is the mantle. So now let's finally get into what that means for us as writers and world builders. So, is there a way to predict which direction a convection current will take a plate? Nope. In fact, there is good evidence that plates can just change direction. So no, there is no way to say where they'll go, just that they go. Is there a way to predict what will be ocean and what will be land? Yes, that one is a yes. The difference between what is land and what is ocean is entirely dependent on the type of rock that the crust is made out of. There are 3 types of rocks in general: igneous, sedimentary, and metamorphic, but for this we really are only going to be discussing igneous rocks. They form from lava, or a liquid which is rising out of the mantle. Before it reaches the surface, it's called magma, but once it reaches the surface, it's lava. Technically, you can get stuff forming from magma, but we're going to mostly be talking about lava. The distinction between those two is a little bit more famous because it's a meme a la mitochondria as the powerhouse of the cell. We all remember our middle schools teaching us that lava and magma are the same thing on different sides of the crust. But anyway, igneous rocks. There are 2 major categories that we care about for the crust: the felsic rocks and the mafic rocks. Felsic rocks are a lot lighter, both in color and in density. They have lots of silicon, sodium, and minerals like quartz, lighter feldspars, and muscovite mica. A really recognizable example of a felsic is granite. The mafic rocks are a lot denser and darker because they are made out of the iron and magnesium-rich minerals like olivine, you remember, like from the mantle, and the calcium-rich feldspars. So these are a lot heavier and denser and darker. So you've probably heard of basalt. The oceanic crusts are typically made of basalt. Denser ocean plates tend to be much thinner, and also since they are so much denser, they tend to float lower in the asthenosphere. This way they are literally at a lower elevation than most of the continental crust, which are both thicker and less dense. So if you drain the water from the world, you would see these huge rises where the continents are, and that they are so much taller than the oceans. Rain the waters back down, and they'll all flow to the lowest points, which is the oceanic plates, and the oceans will just come back down where the waters can get closest to the gravitational center. Now the fun thing is, you can literally pick which spots are which. If you just grab a sheet of paper and mark out like random shaped blocks to represent your plates, you can just select a direction that it's moving in, and whether it's oceanic crust or continental. It's the interaction between these 2 basic pieces of information, plate type and direction, that results in the rest. So the places where the plates interact are called boundaries, and there are 3 types that you really need, because there are only 3 types: divergent, transform, and convergent. Let's start with divergent boundaries. This is where plates are moving away from each other. At these places, you always see new oceanic crust forming. As these 2 plates shift away from each other, pressure lessens on the mantle below, which allows for more magma to form and rise up. This specific melting process allows for all of the mafic materials to get added into the magma, which makes it denser. Oceanic rocks do include materials to make granite, but it's the presence of extra olivine and calcium feldspars that make it heavier. All mafic and felsic rocks contain quartz and lighter minerals, but none of the felsic rocks contain the heavy minerals. So these decompression zones produce ocean floor because of the way that the different minerals are able to melt into magma. Depressurization makes it easier for the heavy minerals to melt. Now this is even if it's 2 land masses moving apart, like you see in Iceland. Those rift valleys mark where the North Atlantic plate is separating from the Eurasian plate. And if you look at the North Atlantic plate, actually, you'll see that it's about 1/2 ocean and 1/2 continent. North America is on the same physical lithosphere plate as half of the Atlantic Ocean. Continental crust and oceanic crust can be built on the same plate, which is why it is very important to distinguish between the plates and the crusts. Now, divergent boundaries have way more volcanoes and separate in different stages. Early steps are on-land volcanoes and a valley forming at the rift. Then that valley just continues to get wider and wider as it starts to fill in with water. The rift itself continues to have a bunch of volcanoes and mountains, but at that point, the land masses will move away from the volcanoes and mountains. So all of that cool stuff is now under the sea, which is what becomes a mid-ocean ridge. The continents then drift apart as the plates just grow between them. Take a look at Iceland, actually, if you want a sense of how that young rift valley looks, because it's one of the best examples we have. Now, very briefly, I'm going to discuss transform boundaries, which is basically where 2 plates are sliding past each other. No matter what they are, this is going to lead to earthquakes and actual sections of the land splitting away from each other, like the San Andreas Fault. They're very cool, but they don't cause any structures, really. So these are just more important for future episodes about earthquakes and other geological events. Now, the most complicated are the convergent boundaries. This is where 2 plates fully collide into each other, and there are a few ways it can go down depending on what type of crust is colliding. The first and most common is for oceanic crust to run into continental. This forms what's called a subduction zone, a zone in which one plate gets pulled underneath another, or pushed. Nobody's quite sure, and there are 2 camps and they fight a lot, so I'll say both words. Anywho, an oceanic plate is much more dense, sitting lower in the metaphorical waters of the mantle, so it's going to shift underneath the continental plate. The oceanic crust then starts turning back into the mantle plateau as it gets superheated, but not without some cool stuff happening along the way. First, these areas where one plate dips dramatically underneath another leads to massive trenches. Think about the Marianas Trench over by the Philippines. It's kind of like that, except for that trench is technically between 2 oceanic crusts. But yeah, if you want massively, horrifyingly deep holes in the ocean, they actually happen not too far off from shore. Open up a satellite view in Google Maps and just look at how dark the waters are all along the Asian side of the Pacific Ocean. Those are trenches from the massive amounts of subduction zones as the Pacific Ocean spreads apart into Asia and the Americas. Other than trenches, you get some cool mountain action going. Remember how I said lowering pressure on the mantle will cause it to melt into magma faster? Well, that's only one sort of accelerant to the melting, called decompression melting. Then there's the usual, just add more heat and it'll eventually melt, but it takes tons more energy than the other two methods, because there's also the addition of a flux, which is also called a volatile. Water is actually a volatile. It dramatically lowers the temperature and pressure needed to melt the mantle, leading to lots more magma production when it's involved. And wouldn't you know, but when you have a piece of ocean getting sucked down, some water will inevitably get dragged down with it. This increase in water leads to much more magma bubbling up underneath the continental crust, like the Andes Mountains in Chile. As the Nazca Plate is getting pushed away from the Pacific Ocean ridgeline, and it sinks underneath the South American plate and slowly pushes new continental magma up into the mountain ranges, often with some volcanic action included. Not really as much volcanoes as divergent plates, but it does happen here, which is also actually how we get the Cascade Mountains and Mount St. Helena. Convergent boundaries also potentially cause island arcs, where a series of volcanic islands form along a convergent boundary, as long as there's a subduction zone. So something like the Antilles or the Solomon Islands, among many others. Island arcs may be one of the only really cool things about oceanic on oceanic convergences other than trenches, and massive tsunami-causing earthquakes. Island arcs can form in any subduction zone and can actually lead to new continental crust, although the process does take ages. But nothing makes mountain ranges, and I mean nothing makes mountain ranges, like a continental plate hitting a continental plate. Oceanic crusts hitting each other can be kind of boring, like one will go below the other and sometimes maybe they'll switch back, but one will always go down. The oceanic plates can technically go either up or down depending on what they hit, but continental plates must always go up. Where oceanic convergences can make trenches, continental plates create the Himalayas. Neither plate sinks, so instead all of that rock just goes straight up, and boom, you have your giant, snowy-capped, stony mountains. Now, these do not have volcanoes, like ever, but they do have extremely intense earthquakes. So maybe put your volcanoes elsewhere, because you can have a hotspot or a different type of boundary. I will eventually have a volcano episode if you would like one, where I can talk about good ways to build volcanoes and types of volcanoes. Now, I could technically start talking about aging mountains and the concept of the rocks at the bottom getting metamorphosed and turning into new types of rocks, or other types of rocks getting thrown into the mix and building on top of mountains and between mountains, but that would be spoilers for our interview, so I'm gonna let my guest today get into that later. And I want to get to the idea of fantasy now, please. So, what all of this is trying to accomplish is avoiding the Mordor conundrum. I realize that this episode is airing on the anniversary of Tolkien's death, and I'm about to rip on his geology. Let it be known that I have the utmost respect for Tolkien and his writing and his storytelling, a little less so his geological know-how. I love the man, but here we go. If you're making a fantasy setting, chances are you like the genre, and through a series of deductions, I'm going to assume that you know the general geography of Middle-earth, even if just vaguely. So let's try and apply what we just learned to Mordor. It's a literal box of mountains that make approximately a rectangle minus a side to the east. These are actually considered to be two mountain ranges. The northern ones are called the Ash Mountains, so maybe they're volcanoes? Except he only says that there's one canonical volcano, and it's Mount Doom, isolated in the south. And then there are the west and eastern mountains that are an L-shaped range called the Mountains of Shadow. All of these do have elven names, by the way, because Tolkien was extra like that. These ranges, however, don't make any sense because he wasn't extra like this. So how did they form? Geologically speaking, according to Tolkien, it was gods, but geologically, how could they have? Well, according to William Anthony Swithin Sargent, now that's a name, In an article trying to work this out, mortar would basically have to be its own plate, a very small baby continental plate that's getting pressed in on by other plates from the north, south, and west, causing convergent boundaries from all edges, which is technically possible, all things considered, but the amount of minuscule plates getting forced together or torn apart to make these arrangements work out is really quite absurd. Just the amounts of faults, of boundaries, all of them just stacked up on each other in such a small space feels a little overdone when you're trying and read through the charts in this guy's report. Our author of the report with a very long, cool name actually has this out as a PDF online titled The Geology of Middle-earth if you'd like to check it out. But of course, Tolkien explains the existence of mountains with the wrath of Melkor, essentially his Satan figure, so we can't really claim that anything in Middle-earth formed naturally. He has his mythology to cover his back, but this makes the geology reliant on the myth and religion. In The Lord of the Rings, as the gods seem less involved, it's hard to explain how it all formed naturally. Even New Zealand isn't this densely populated with plates and intersections. I would develop my maps based off of plate tectonics, so even if the gods were to disappear, it would all look like it perhaps could have formed independently. Also, I just like the idea of my map actually making sense, personally. So what I do is I mark out the plates, their directions, what types of crust are in different spots, and determine what structures should go where depending on the boundaries. Or if you already have a map made, just take a look at your mountains and volcanoes. Where you put them should technically have certain types of boundaries, and now you can add whatever other features belong in that region, and also maybe take the volcanoes out of your continental and continental convergence. And if you do want to just have crazy mountains everywhere and say it's gods, valid, go for it. Make them look really cool, give those structures some real characteristics, and when we get to religion and talk about world creation, we'll definitely start talking about that. So, go wild. As for if you want to do it scientifically, I am giving you information that I learned from watching the Earth and Space Sciences ex-professors uploaded lectures on YouTube. So, why don't we talk to somebody who actually is a professor and has studied and taught these exact concepts for a living? Thank you so much for joining me on the first proper episode of From the Void Up. I am very happy to have you here. Would you introduce yourself really quickly?
Yeah, my name is Dave West. I'm a professor of geology at Middlebury College. I've been at Middlebury College since 2001 and have been teaching classes here and doing research in the Northern Appalachians since that time.
Very cool. So could you tell us a little bit more about what exactly it is you study? Do you have a specific title for your field, and what sort of research do you collect?
Most of my work is in bedrock geology, so studying exposures of the crust of the earth, which record a record of the geologic history of the past when those rocks formed. Most of my work has been in the Northern Appalachian Mountains. Specifically, a lot of it has been in mid-coastal Maine, in that region, because the bedrock is very well exposed there. This is all part of the Northern Appalachian Mountains, which are an older mountain range, more deeply eroded, but it provides kind of an ancient analog to active mountain ranges like the Himalayas and the Andes. So even though the areas that I'm studying aren't presently tectonically active, the rocks that are exposed there are a product of ancient plate tectonic activity. So in some ways I study plate tectonics, but study it in old rocks, trying to basically reconstruct the plate tectonic environments of the past based on the rock record that's preserved in this older mountain belt.
That's really cool. So that sounds like the data collection might be kind of interesting. It's partially eroded, so how much can you actually identify by eye, and how much of these different types of rocks that you're focusing on are you using technologies to analyze, and how much can you just see visually?
Yeah, that's a great question. So all the work begins with field work. So I go out and walk around looking for places where bedrock is exposed. And again, Coastal areas are great because we all know the rocky coast of Maine and we see all those rocks there. So there are a lot of observations and measurements that can take place in the field. What kind of rocks are there? What are the orientations of the rocks? And then samples may then be collected and brought back to Middlebury College. And that's where there can be some more sophisticated analyses done. So you can crush these rocks up and analyze their chemistry. And the chemistry of the rocks, the details of the major and trace elements in the rocks can tell you something about how they formed. You can also separate minerals from those rocks that have radioactive elements in them, and you can use those for radioactive age dating. So you can determine how old those rocks are. So combining some of the field observations and measurements with more sophisticated geochemical and geochronological techniques can provide a fuller picture of the past of these old rocks that are exposed in that area.
So why don't we get into a little bit of the details of what this research you've been doing has actually brought up?
Yeah, one of the more interesting studies I've been involved with over the years are looking at ancient faults. So we know there are huge faults like the San Andreas Fault in California that are active and periodically experience significant earthquake activity that is incredibly disruptive to people and does a lot of property damages and costs lives all over the world. And there have been some huge earthquakes in the past. Most of these earthquakes, the actual seismic energy that's released occurs 10, 12, 15 kilometers underground. So we can pick it up with seismic equipment. We know where the energy is coming from, but you can't actually get down there and see what was happening, where that earthquake actually originated. So that's where studies of older mountain belts can come into play, because there you've eroded off the top layers of the rock. So even though the faults aren't active anymore, you're seeing basically the eroded roots of those faults that were active millions of years ago. So actually it would be like going to the San Andreas Fault and drilling a hole 15 kilometers down and going down there and looking at it. So that's in my mind, one of the cool aspects of some of the research is that you would think studying an older dead mountain range would be kind of boring, but what it is it's kind of a fossilized lower level look at the tectonics. So a lot of what happens during plate tectonics is happening underground. We're only seeing a small two-dimensional surface at the Earth's surface, and a lot of what's happening is deep underground. So by studying an older mountain belt, you basically shave off the top number of miles of rock over millions of years of erosion, and then it's all kind of laid open for you to look at. So that's what's kind of cool. You're sort of studying the guts of this old mountain belt that used to be active, but you're looking at the deeper parts of it. So it's not quite as exciting now. I mean, I don't have an earthquake going off. I mean, I don't want an earthquake going off, but maybe a little rumble here and there might be kind of cool. And there are not any volcanoes erupting, but they're ancient earthquake rocks in areas that I study. They're ancient volcanic rocks in areas that I study. And so that looking at these older ones can actually yield information about modern processes.
So what do those then look like after they've aged over some time? Like if somebody was writing about a mountain range that was older, what sorts of identifying features would you be able to describe and see in different settings?
Yeah, I mean, one of the things is you can see rocks that are just kind of mashed and deformed. We think of rocks as being, these rigid, solid, brittle things, but when they're deeper underground, they actually behave like silly putty. They actually flow. So you can see rocks that have been squeezed and pushed up, and you can measure the geometries of a lot of these features and infer what the stresses were that produced those particular features. So I think a lot of times the layperson, if they looked at the rocks, you would see that they're, instead of being flat, most rocks when they originally form in flat layers parallel to the Earth's surface. But now when you go out there, you see they're all flipped up. They're nearly vertical. You'll see folds. You'll see places where magmas have intruded, molten rock has cut through. So it definitely looks different from what you might see in the Andes with a volcano, because if you're looking at the eroded roots of it. So you see a lot of bent, broken rocks, a lot of things that have cut through there during millions of years of geologic history.
Are there any like specific processes that always result in specific features and looks to the rock, or is it really variable? Could you essentially design it to however you want?
Yeah, I mean, there's certain, like I was talking about in terms of earthquakes and faulting, there are certain types of rocks that only form in those environments. There's a kind of a weird rock that I've been involved in studying. It's called pseudotachyllite, and it's actually a frictional melt product. So when you have an earthquake, the rocks may move so quickly underground that it actually melts material, and then that melt essentially gets frozen underground, and you can see it and identify it later. So you can find these kind of paleo melt earthquakes from deep underground. So that's kind of cool. And certainly a lot of plate tectonic activity results in the production of magma, molten rock, and eventually volcanoes. So, in the Andes, there are plenty of active volcanoes. In the Pacific Northwest of the United States, there are, Mount St. Helens and Mount Rainier and things like that. Those are volcanoes. But the reality is the magmas that are produced, only about 10% of them actually erupt at the surface. Most of the magma, when it's traveling up through the Earth's crust, because it gets colder when it gets closer to the surface, it actually freezes underground. So there's actually a richer sort of catalog of those magmas deep underground that have frozen before they erupted from a volcano. So by looking at those older sort of frozen volcanic rocks that froze underground, you can get a lot of information about the volcanic processes that were occurring in that area. So I think plate tectonics, it results in a lot of magma production, which is usually people mostly associate with volcanoes, but again, a lot of that magma never makes it to the surface. And then the other thing are the earthquakes, which is a product of the stresses and the uplift of the mountains and things like that. So those are the kind of things that you can sometimes identify in the field pretty easily.
Yeah, because especially earlier in the episode, I talk a little bit about subduction zones versus convergent plate boundaries that are just continental on continental, and the extreme mountains that form out of those. And then I was looking at the map that you sent me, the geological map of the region that you were studying, and it mentions partially that there was at one point a subduction zone with an oceanic plate, that then the oceanic plate essentially got entirely destroyed, and that's what brought the island chain up against the continental. Is that like a frequent process where it goes from one sort of boundary to another just by that movement?
Yeah, and that's one of the cool things about studying a mountain belt like the Appalachians. I mean, it formed over a period of hundreds of millions of years, and there have been evolving plate tectonic processes over that time. So humans are only looking at a very tiny instant of geologic time while we're here. So we're seeing basically a snapshot. But when you look at older rocks, you actually get a much longer history. And the plate tectonic setting changes dramatically over time. I mean, if we went back 50 million years ago or 60 million years ago, there was an ocean that existed between India and Asia. And that ocean was eventually subducted away, and India collided with Asia, and that created the uplift of the Himalayan mountain chain. So that particular area went from being basically an ocean to essentially being a major mountain range. And that's happened repeatedly in a mountain range like the Appalachians, where we know from the geological record there were periods of subduction, there were periods when things were colliding, then there were periods when it pulled apart again. And so it makes it challenging because you've got a lot of different tectonic environments superimposed in a single area. So if I go to the Himalayas right now, I know that's the product of continent-continent collision. If I go to the coast of Maine, well, at one point it was subduction, then there was collision, then it pulled apart again, then there was another collision. So you're kind of untangling multiple events. So the Appalachians, as I said earlier, formed over hundreds of millions of years in multiple episodes of tectonic processes. And so it's a very old, complex mountain range that's been sort of, the way I think of it's been kind of partially decapitated because it's eroded off and you're sort of seeing the roots of it. So it provides endless challenges for folks like me that are trying to reconstruct what happened.
I can imagine. Then if everything's like eroding away, Are there any predictions as to what it might have looked up before that erosion happened, like different stages of growth that it might have gone through?
Yeah, that's a great question. One of the things that a lot of people have speculated about were how high were the Appalachians? Was it a Himalayan type mountain range? Was it an Andes? And it can be a little bit tough to figure out, because we do have a lot of sophisticated techniques that I can pick up a rock at the Earth's surface, and based on the mineral assemblages and the chemistry of those minerals, it'll tell me how hot that rock got and how deep it was underground, what pressures that it was subjected to. So you can kind of use that to get an estimate of how much material was over the top of some of these rocks. The difficult thing is that a mountain range kind of erodes like a melting iceberg. So, an iceberg has a big root to it. I mean, most of it's underwater, and a mountain range is the same way. A lot of the mass of a mountain range is actually underground, deep going into the mantle. And so when it erodes off the top, it's actually kind of feeding up from the bottom, just like, if you had an iceberg and you were melting the top part of it, the bottom part is kind of feeding it up as well. And so a mountain range erodes the same way. So some of the rocks in Vermont, for example, we know were 10 miles underground. That doesn't mean the mountains were, 10 miles high. What is that, 50,000 feet or whatever? But it just means that through that process of erosion at the top and feeding up at the bottom, that's how much material has been excavated off the top. But most people, I think, acknowledge that it certainly had elevations that were probably comparable to the Andes. Maybe not Himalayan elevations, but certainly 10 or maybe even 20,000 feet high in terms of the elevation of the mountain ranges. But a lot of it's been, worn down now, obviously.
Yeah. So a lot of the features that I also noticed on the map that you sent me were the dikes and the fault lines that were specifically mapped out. So do dikes ever have like a consistent way of predicting where they'll show up? I understand they go through like weaker points in the rocks, but do we often know specifically where that'll be? And are there any ways to determine what section's going to be the weakest part just from how they form?
Yeah. As I mentioned earlier, a lot of the rocks are layered, so they might have originally formed as sediments on the bottom of the ocean floor, so maybe sand or silt or clay lays down on the ocean floor, and it forms what we call beds. There's just these layers. And then during the plate tectonics, the rocks get squeezed and a lot of those layers get tilted up. And so those layers represent points of weakness. And so the magmas can go through the layers in the rocks. The other thing that happens is that if there are stresses on the rock, so if you're pulling apart a rock, you're going to start to crack it. So you could imagine if you had a big piece of ice or something and you were trying to pull it apart, it would crack through the middle. So when their stress is acting on the rocks, they'll form cracks. And then if down deep there are magmas forming, those magmas will then facilitate the cracks. So what we can do is we can actually measure the orientation of the dikes and think about what stresses would have been present to facilitate the intrusion of those dikes in those orientations. So, for example, if I see a dike that's oriented in a north-south direction, that suggests that the pulling apart was in an east-west direction. So you imagine if you pull apart in an east-west direction, you're probably going to make a crack in a north-south direction, and then the magma is going to come up through that crack. We can use the orientation of the dikes to kind of backtrack what the stresses were during the formation of the dike. So that's a great example of kind of a multifaceted study. What's the chemistry of the dike? That would tell you something about the plate tectonic processes that produce the magma. What's the orientation of the dike? That tells you something about the stresses that were in that area. What's the age of the dike? That tells you the time that those stresses were acting on the rock, because then you could have another dike 50 million years younger that cuts across at a different angle, telling you that the stresses were going in a different direction. So those igneous intrusions, those dikes can be quite informative in terms of backing out the geologic history.
Yeah, that sounds like it.
Yeah, and I think one of the things that I've benefited from over my career is that I've looked at ancient mountain belts like the Appalachians, and then I've gone to places that are more active. So I've been on field trips in the Andes. I've been to parts of the San Andreas fault system. I've done some work in Jamaica that's along the same fault that the earthquake occurred in Haiti it's helpful to look at modern processes and then go back to my old tired rocks and try to infer processes. So I think that's one of the main things that I do is I think looking at the old rock record, trying to infer what sorts of processes were active in those ancient times that formed those things. And that can shed light on modern processes.
Mm-hmm. And then could you just elaborate a little bit more on like what types of rocks you would see and how they look for anybody who would want to describe an accurate revealed root of a mountain?
Yeah, I think a couple different things to look for. One are the dikes that you mentioned. So a lot of times you can see very light or dark colored rocks that seem to be just like cutting across or knifing across other rocks. So those are, when you see that, a lot of times, those were that liquid magma that was making its way up through cracks in the rock. And maybe some of it eventually erupted in a volcano, but what you're seeing there is the plumbing system of the volcano, those cross-cutting dikes in there. The other thing that you might see is this layering that I was mentioning, that a lot of the rocks have thin layering that it may be only a few inches wide, so that when you walk along parts of the coast or in other areas, you'll notice some really regular layering in the rocks. And those could be the original sedimentary rocks, or more likely in an older mountain belt like the Appalachians, those rocks have been cooked. They've been deep underground, so they've been metamorphosed. So that layering represents the stresses, the orientation of the stresses, and the metamorphism.
Yeah.
Looking at the rocks from, a number of, meters away, you might see those cross-cutting dikes and things that are coming through that represent those ancient magmas that froze underground. And then you might also note the layering, the real regular systematic parallel layering in the rock, which probably represents the original sediments in the rock, but then have been metamorphosed. And then if you have an opportunity to get really close to the rock, which is where I think a lot of the fun is that you can see different minerals in there. And so a lot of times places like the coast of Maine, there are lots of nice garnets and tourmaline crystals and things like that you can see. So I always tell students, don't be afraid to get close to the rock. It's not like we're studying lions and tigers and bears. It's not going to attack you. So that's, one of the benefits of studying something that's old and dead. You can just walk up there and put your nose down to it and look at it really closely, which is kind of cool. So, and by doing that, you can get a very different perspective and see different minerals. And as I was saying earlier, we bring these rocks back and we can look at them under the microscope and see some even cooler stuff at that scale. So there's a lot of different scales of observation. We can look at things with satellite imagery. I can get out there on the outcrop and look at things in sort of a normal megascopic way. I can look at things with a hand lens, with a magnifying glass, and then I can bring it back here and look at it under a microscope. And then we have a scanning electron microscope downstairs, and we can magnify it 10,000 times and look at it there. So the different scales of observation, I think, are really cool. And at each scale provides some information and can provide more detail about the history of the rock. So I would say, that's a long-winded answer to your question about what you might see. A lot of it depends on the scale. You can look at a map and just see the orientations of, like in Vermont, the Green Mountains are north-south directed. Lake Champlain's a long north-south lake. That's because everything was squeezed from an east-west direction. That's what created that grain. So you can see that at a map scale or at a large mountain scale, and then you can also see that down at the microscopic scale, which is kind of cool.
That does sound really cool. I am so excited to get to Middlebury next year.
Yeah, it'll be fun. It'll be fun. Yeah, and I wish I could take you out to see the stuff, and it's a lot more fun. That's one of the fun aspects of geology, is that you can actually, the best way to learn about it is to see it firsthand. It's just to actually go outside and look at the rocks and point around and speculate about them and collect samples and bring them back here and look at them at different scales. So it's quite a fun way of studying things, in addition to providing a lot of interesting scientific information and practical information about earth hazards and resources and environmental geology, which are also obviously really important.
Yeah. And potentially my major. So
yeah, cool.
That'll be fun.
Yeah.
just to wrap up, are there any misconceptions that you want to have a chance to clear up?
Yeah, I think in Vermont and a lot of the areas I study in Maine, I go out in the field and people are saying, oh, you're going to find some gold, or you're going to find some oil, or you're looking for dinosaur bones or stuff. And I think there's kind of a misconception about geologists and what we do. I mean, there's certainly people out there that look for resources like that, but geology is a very diverse science. And so there's a lot of aspects of environmental geology and aspects that are more societally relevant than what I think a lot of people sort of might have a preconceived notion of what a geologist do. I mean, it's a very sophisticated and broad science. So it's not just a bunch of old guys running around with a hammer banging on rocks. I mean, I do that, but most geologists don't. I mean, a lot of geologists never go in the field at all. They're just doing a lot of the detailed studies of samples that come back, or they're looking at remote imagery, or they're looking at features on Mars and trying to figure out how they formed from the phenomenal imagery we get there. So I think if there's a misconception, it would be more in terms of a misconception of what a geologist is, because it's a very broad term. We do lots of different things. There are lots of different kinds of people who do geology, and it's fun in that sense, in that it's so broad. And I think it can then be welcoming to a larger population of people with different expertise.
That makes sense. All right. Thank you so much for joining me.
Cool.
This has been really fun, and I really appreciate you coming through for the interview.
Yeah.
I think this has been pretty good.
Well, thanks for having me, and I appreciate it, and I apologize if I was a little long-winded with stuff, but I get kind of excited about talking about it. So
That's perfect. I just want to say thanks again to Professor West for speaking with me in this first ever episode of From the Void Up, and also for talking a lot more in depth about how mountains actually look rather than just how they form. And he did say the best way to learn about geology is to look at it. So my homework for you all is to look up different kinds of rocks. Take a look at granite and figure out how you would describe it. I mean, now you know where it goes. The next step is how to explain it. And metamorphic rocks, you can look those up too. He explained that they are often deeper underground, unless of course it's an exposed older range. Gneiss rocks, spelled Gneiss, are rather nice to look at. So check out all of these different geological features at a slightly closer scale to really give some character to those rocky outcrops with brightly colored layers that are technically possible. I'll be posting some visual guides on the Instagram, Twitter, and Facebook pages if you're not sure where to start. Just check out From the Void Up on almost any social media platform and I'll be posting there. These recordings are also being uploaded to a YouTube channel named, you might guess, From the Void Up. On YouTube, I can add captions for anyone who needs them, and I'll also be compiling playlists of other people's lessons if you need further information, like that Geology 101 course I skimmed, or piles of explanations on the Coriolis effect, which you will probably need for next week. And of course, if you have any questions about your setting in particular, feel free to shoot me an email at fromthevoidup@gmail.com or DM me on your preferred social media system. I'm more than happy to look into anything you might need backup research on. Or hey, if it's a big enough question, I'll just add it to the research list. Thank you for listening to From the Void Up. Subscribe to this podcast with whatever streaming site you use and leave a review if you liked it. Or if you didn't, honestly. The more feedback I get, the better this thing can get. Special thanks to Jerry Ritigliano for the theme music, Dylan Desmarais for the cover art, and again, Professor West for being my guest today. I have been your host, Tyler Hadar, and in the meanwhile, keep on building. I'll see you all next week.